This is an Algebra 1 lesson on exponential growth and decay. We'll talk first about interest, say in a bank account, something like that. For example, you go and put money in a bank and they're going to pay you interest on your money, which is kind of like rent. You rent your money to them, you leave it there for a while, and they do other things with it like loan it out to people, and they pay you for using your money, and that's called interest. Here's an example with compound interest. This is how most interest accounts are at banks. So for example, you have $100 and you're going to get 10% interest. So during the first year, you have your original $100, you earn $10 rent or interest on your money, and at the end of the year you have $110. Okay, compound interest is interest that's based on the original amount and on the interest previously paid or earned. That comes up in year 2. In year 2 now, in your bank account at the beginning of the year is $110, which represents the original amount you deposited of $100 and the $10 that you were paid in interest the previous month. You now get 10% of that, not of the original. So you get $11 this year for a total of $121. Again, the third year. Now you start the year at $121. You get 10% of that, or $12.10. Again, that's interest on the original principal and the accrued interest, 10 and 12, for a total of $132.11. Again, compound interest is based on the original and whatever's been earned on it each year. By the end of the fourth year, you have $145.31. Simple interest, on the other hand, is not usually paid by most banks anymore because people wouldn't put their money in because they can get more elsewhere. Simple interest is based only on the original principal amount. $100, the same example. So this is the same for the first year. $100 is deposited, $10 is earned, for a total at the end of the year of $110. The difference here is that
Hannah Ahmed.
Okay, Hannah.
To the front office. Hannah Ahmed to the front office.
Okay, the difference here is at the beginning of the year there's still $110, but you only earn $10, 10% of the original amount for the total for the year of $120. Same deal, each year you only earn $10. You only earn interest on the original principal amount, not on any earned or accrued interest. So the total here would be, after 4 years, $140 as opposed to $145.31 with the compound interest of a similar scenario. So you make $5.31 more just because of the way that the interest is calculated. This is a form of exponential growth and decay. This one is growth, obviously. Our first, let me show you the definition, not the definition, I'm sorry, the equation that gets it for us. Exponential growth over time is y, which is for yield, equals the initial amount times 1 plus r raised to the t power. What are these things? The initial amount is here. The growth rate is r. That's typically going to be a percentage. In our previous example, that would have been 10%, the annual growth rate. Add it to 1, and then you get, and then to the time. For this particular form, the time can be in any units. It's typically in years, but it can be in other units as well. And that'll be fine as long as you're consistent with it. We call the portion in the parentheses the growth factor. It's what's multiplied by the initial amount. Thus, factor is the word we use for multiplying something that is multiplied. Let's see what this looks like after 1 year. Say with our $100. $100 is the initial amount times 1 plus the rate. We can't add a percent to a whole number. It's got to be a decimal. So we'll change our percent, 10%, to 0.1. and then raised to the 1. We'll do it for 1 year and see what happens there. Sometimes kids say, why is that 1 there? Well, this kind of shows us why the 1 is there. If we use our distributive property, this will be 100 plus 10, which is exactly what we just did with our draw it out by hand example of interest. So in the growth rate already is included the original amount and the interest that's being paid. Now it will vary over years as the method that I just showed you. But this gives us a concept here that we're including the original amount in so that when we're done and we have the yield or the final amount, it already includes the original. Some interest calculations are separate. You'll have the original amount and then you'll have the amount earned in interest and you add them together to get the total amount in the account. Here it's already included. So if, for example, on my compounding here, I wanted to know how much interest was paid, I could add up this column and that would give me the amount of interest that was paid. Or if I were using this formula, I would come out with 145.31 and I would then need to subtract the original amount 100 from it to find out that there was $31 paid in interest, about $31. Okay, this is exponential growth, and the bankers just want to talk about exponential growth over time. They don't want to talk about exponential decay over time, because exponential seeing those together here, exponential growth with a plus, exponential decay with a minus. All of the items mean the same thing. Just a note for if you see it in other circumstances, math is used like everywhere. And in math, we need to accommodate all the different folks and all the different disciplines that need it. This is the same formula that the bankers will use, except they like to say A for amount instead of Y, and they like to say P for principal instead of A for initial amount. Other than that, they use it the same. And so they'll be talking about the amount that comes out rather than the yield, and they'll be talking about the principal, which is the original initial amount that's deposited. And they're only going to talk about plus. You notice I didn't put the banker's terms here because they don't want to talk about minus, because that means losing money. And people don't come to the bank and say, would you please lose my money for me? No, they don't do that. Okay, here's an example. Let's look at how the formula works. In a bank account, say you deposit $200, you're going to leave it there for 3 years, and you're going to be paid 4% interest. How would that work? We go, here's our formula, y equals initial amount times the rate factor, growth factor time, raised to the time. Okay, 200 is the initial amount, 1 plus the interest rate written as a decimal. This will work here just fine, and that you punch it in the calculator, and that's what you come out with. A word about the calculator use on this: if you're using a TI-84 calculator to do this, you want to make sure you know how to enter powers other than squared. When you're using squared, there's a dedicated button right here that you can automatically square things. But in interest, you're going to frequently want other exponents. So how you would put this into the calculator would be 200. Can you see that? Does that show? There we go. 200 times parentheses 1 plus 0.04 close parentheses. Now you need the third power. So the third power is the caret button right here. The little rooftop. Raise to, and it raises it up, and then you punch in what you need. So that gives you the whole thing right there in the string, and you can see it. Hit enter, and it'll tell you the amount. Bankers tend to round down. If you don't get earn the penny, they don't give it to you. So that would be for that one. So that's how to use calculators to do it. Here's another example. So that'll be $5,000 initial investment or initial deposit, for 10 years at 8% interest. Y, the yield equals 5,000, the initial, times parentheses 1 plus 0.08, that's the growth factor, raised to the 10th power for 10 years. Put it in the calculator and that you get it. This is an example of compound interest. A couple of words that come up. You need to know the language of all the different disciplines. In math, we tend to talk about growth and decay. Also in science, very often they'll talk about growth and decay. Sometimes in math, we'll just say it's going up or it's going down. And frequently in money matters, such as banking or investments, the words depreciate and appreciate will be used rather than growth and decay. Depreciate, go down. Appreciate, go up. So if you just have the two to choose from, you can remember that you appreciate it when you make money. So that's when it's going up. It's a different use of the word, but it's perfectly allowable in the English language. To depreciate and to appreciate. Here's an example. Read through the example and try to do it, and then I'll put the answer up. Okay, here's how to work it. A word as I'm beginning, per year is one way to say it. Per annum is the same thing. You need to know that the word annum, per annum, is Latin for in each year. Per annum, think of annual like every year, and that can help you remember that annum means year. Frequently, this will just say maybe 7% per annum instead of saying per year. How do we work through this problem? First, it asks us to write a function that models the gas grill shift over time. Okay, start with our form. That's the basic form for growth. It says it's increasing. It's going to get more. It's going to grow. Then I put in the initial value, the interest rate. I haven't put the time in yet because this says shift over time. So this is a general formula that'll do any number of years. Now the next item it asks us for is specifically for 2002, which is 17 years after 1985, so our exponent now becomes 17. We go ahead and work it out, put it in the calculator, and find this. On rounding, on these matters, you're going to have to use your noggin and think about it. Does it make sense to ship 2/3 of a gas grill? Probably not. It's probably best to say 10 million and some without putting the 66 on the end. Depending upon your criteria that you're working with, it might go one way or the other. But I would put that here the best answer is 10,022,920 gas grills having been shipped in 2002. So notice I did not round up. I truncated to the total amount that were shipped, the total whole amount that were shipped. Here's another problem. Read through it. Try to work it. Pause. Here's the answer. Worked out. Let's look at it. Okay. Again, I put the form. It's always good to write the formula. That way you make sure you get it right. You notice that it's increasing, so it's going to be exponential growth, not decay. Here's the formula. I write in 900 times, it's 900 million, so you have an option here. You can say 900, and remember at the end it'll be millions, and you'll need to adjust it. Or you can go ahead and put the million in, and at the end you won't have to adjust anything. Depending upon how big your numbers are, it won't fit